This is lecture 210 on quadratic models. We are using the student note packet. Page 19 is where you'll take the notes for this lecture. Part of the homework assignment will also be to finish the nonsense review, which is on page 20. So if you just turn the page, pink section, page 19 is notes today. Part of the homework will be page 20 plus the bookwork. So you need a graphing calculator today. We're going to be graphing some of the functions that we write equations for, and then you'll do the homework questions the same way. So here's the situation. We've got an ellipse with the equation 4x squared plus y squared is equal to 64. And we're told the following about this ellipse. It's centered at the origin. It extends 4 units on either side in the x direction. So that means we're going right and left 4 units, and then 8 units on either side in the y direction, which means from the center we'll go up and down 8 units to get the top and the bottom of our ellipse. We're told that a rectangle is inscribed in this ellipse, and we want to write all the answers in simplest form. So the first thing we're asked to do is graph the ellipse and the inscribed rectangle. So let's do that, and then we'll do the second part of part A. Next semester, we will have a conics unit where I would give you the equation of the ellipse, and you guys would actually have to graph it without me telling you up 8, right and left 4. So you guys would be able to look at that equation and actually be able to identify how to graph the ellipse. But that comes later. Okay, so 4 units left and right to get to the outer bounds on the x-axis, and then up 8 and down 8. All right, and then I'm just going to sketch in the ellipse here. Looks something like that. I have trouble drawing ellipses that don't look lopsided. And then we're also told that there's a rectangle inscribed in this ellipse. So we're going to make sure we draw in a rectangle on the inside of this ellipse. Looks something like that. All right, note that I could have drawn a rectangle that looked different than this. So maybe you drew a rectangle that looks like this, right? Is not as tall, but is wider. Or you could have drawn a rectangle that maybe looked like this, super skinny, really tall. Okay, we could have drawn one that was like really short and long. There are many different options for rectangles that we could inscribe in this ellipse. And the point of a problem like this is to actually be able to write a function that represents the area of any one of these rectangles based on one of the coordinates, specifically the x-coordinate for this problem. So that's our goal eventually, is to be able to come up with an equation that expresses the area of any one of those rectangles based on one coordinate, the x-coordinate. So that's part A of part A. The next thing part A asks us to do is then identify a point, we'll call XY, in quadrant 1 that's a vertex of the rectangle and on the ellipse. So essentially, go to quadrant 1, we want to pick the point where the ellipse and the rectangle touch, and we'll call that point XY. Again, we call it XY because I could have drawn many different rectangles, so the X and the Y values would actually change depending on what the rectangle looked like. So we want to make sure that we have it as a variable point that can change instead of like hard values, which in this case would be like 2, 6. Okay, so we've labeled that. We're done with part A. We're moving on to part B. So part B asks us to write an equation for the area of the rectangle in terms of the x-coordinate of the point. So we're going to use an equation for area only with the variable x. But before we do that, let's kind of go through this in steps. What do we know about the area of a rectangle? Well, if you think about the area of a rectangle is just base times height from geometry. Okay, so what do we know about the base and the height of this rectangle? Well, I know if that point in the first quadrant is what we call xy, then to get there, we have to go from the origin, x units to the right, and we have to go up y units. So I just marked on the graph what x and y visually look like. Now, based on x and y, I can determine that the base of this rectangle is 2x and the height of this rectangle is 2y. So the area formula in terms of x and y, which is where we're going to start, is 4xy. The problem is when I go to plug this into my graphing calculator, a graphing calculator won't graph this. It won't graph equations in two variables. So I need to narrow it down to one, and we're asked to do that using just x. So we have to figure out how to express y in terms of x. Now, similarly to the way that we did 2,7 and 2,8, we're going to go to the top of this problem, and this problem actually gives us a way to express y in terms of x. I can take this equation, 4x squared plus y squared equal to 64, and I can isolate y and get y in terms of x. We can do that because of the way we've set this problem up. Because the rectangle has a corner that sits on this ellipse represented by that equation, we can use that equation to equate x and y. So I'm going to do that. I'm going to move that 4x squared to the other side, and then the last thing we're going to do is we're going to take the square root in order to get y by itself. And now we have y in terms of x. We've got a way to actually represent y in terms of x. Before we do anything though, I am going to simplify because the question tells us at the very top we want it in simplest form. So what can we do to simplify this equation? Well, I know that 64 and 4 both have a 4. So I can take a 4 out of 64 and 4, and then this becomes 16 minus x squared. And then the square root of 4 is just 2. So this is 2 root 16 minus x squared. That's how we're going to simplify that before we plug it back into the equation. You could also plug it back into the equation and then simplify. So everywhere we see y in that area equation, we're going to replace it with 2 times the square root of 16 minus x squared. Now, please note 16 minus x squared is the difference of two squares. This is 4 minus x times 4 plus x. You cannot take the square root of that. Okay, it is not 4 minus x. A lot of people will do that, but you can't do it in that way because it's 16 minus x squared. They're not being multiplied together. So there's no way to simplify that. We'll just leave it as the square root of 16 minus x squared. All right, so let's replace it in the area equation to get our final area equation. Our final area equation in terms of x and x alone is going to be 4x times the square root, 4x times 2 times the square root of 16 minus x squared. So our final simplified equation is going to be 8x root 16 minus x squared. That's our area equation. All right, sorry for the mess, but that's what we're going to plug into our calculator. So part C then asks us to use our graphing calculator to plot the graph of the area as a function of x and to find the maximum area of the rectangle. So let's move over to our graphing calculator and actually plot this. So 8x times the square root of 16 minus x squared. All right, so I've turned my graphing calculator on and I have typed in the equation into the y equals 8x times the square root of 16 minus x squared. Just make sure you don't get a syntax error or an error in the graph. Make sure the square root sign goes all the way over that 16 minus x squared. And then we're going to change the window. So hit window, that window button, and we're going to adjust the x min, x max, y min, y max. So change your x min to -1, your x max to 5, y min, I would say -1, y max is going to be about 80. And that'll just make sure that we see the graph correctly. Remember that this function is an area function. It represents the areas of all those rectangles. So we only care about positive values of y because y represents area. We don't want any negative values. That's why I'm cutting off the min at -1 for y. So we don't want any negative values. We don't care about that. All right, so if I hit graph, we get a curve that looks like this, and we just want to sketch this. So we're going to go over to the right, underneath where we graphed the ellipse and the rectangle. We're going to sketch this curve, but I'm also going to find that maximum point because the other question in part C asks us to find the maximum area of a rectangle. So I'm going to do that first before I go over and I actually start writing in on the notes again. So to find the maximum, we are going to hit second trace to get to calculate. We're going to go down and we're going to select maximum this time. In the last two lectures, you selected the minimum. but the process is the same. So you're going to set a left and a right bound, use that blinking cursor, move it to the left of your maximum, hit enter, and then we're going to move that blinking cursor over to the right to get the right bound, hit enter again, enter one more time, so you're hitting enter 3 times, and it should jump straight to that maximum. And we're told that the maximum here is 2.828. If your graphing calculator is off in the thousands or 10,000s place, it's totally fine. And then our y value should be 64. So now I'm going to go back over and I'm going to actually sketch this curve and then fill in the answer for part C. So when I sketch this curve, again, we're talking about a function that represents areas. So we don't actually care about any of the negative values. So I'm just going to keep my graph in the first quadrant and I'm going to just do a really rough sketch there. Okay, that's what the curve looks like. If you've got an older graphing calculator, you might not see the drop go all the way down on that far right side of the maximum as much as you see it in my calculator, which is fine. So your graph, if you've got an older calculator, might look more like my sketch on the bottom right side of the screen, and that is okay. I am going to just mark one point that will give me the scale a little bit more. So we said the maximum is 64, and that occurs when x is 2.828. Right? Something like that. So that is enough for the sketch of a graph with your graphing calculator. The question is, what is the maximum area? And I've made it specifically to round to the nearest 7 significant digits. So if you're not familiar with 7 sig figs or sig digs, I guess you can call it, it's just 7 numbers, essentially, is what I'm looking for. So 64, that's 2, so we need 5 zeros. That's 7 significant figures. Okay, 64 units squared is the maximum area. That's what we found. Remember that the y values of this function represent the areas possible. So the maximum area of a rectangle that we can inscribe in that ellipse is 64 units squared. For what value of x is the area the greatest? Well, that value is the x value we found at the maximum. Again, 7 significant figures, so 2 is 1, we need 6 more. 8 to 8, 4 to 7 looks like units. Okay, so that means that the rectangle that has the biggest area possibly inscribed in our situation in that rectangle and ellipse carries an x value of 2.828. So what does that actually mean graphically? Well, I drew the ellipse back in the upper right hand corner. Graphically, remember that the x value is half the base. So the rectangle, if I want to draw it with the greatest area, has an x value of 2.828, so almost like 2.9. If I go out 2.9, that's like here on the x-axis. If I construct a rectangle that has that x coordinate of 2.9, that is the rectangle that carries the biggest area possible. All right, so not tall and skinny or short and wide. It's kind of more one that fills up the whole ellipse. That's what that looks like. So then part D asks us to write an equation for the perimeter. So we found an equation for the area. Now we want to talk about perimeter. So again, I'm going to start with what we know about perimeter from geometry. Let's talk about perimeter in terms of the base and height or length and width. I guess I used base and height in the last example, so I'll use it here too. So start with the equation for perimeter from geometry and then fill in what we know. Well, what did we know about the base of this rectangle? We knew the base of this rectangle was 2x, and we knew that the height of this rectangle was 2y. So the perimeter in terms of x and y, and I'll write it like that to make it more clear, is 4x plus 4y. But again, we can't plug that into our graphing calculator either because that is in terms of both x and y. We want the perimeter equation only in terms of x. So we've got to go back, use the equation for y in terms of x, and replace it in this perimeter equation as well. So we're going to go back to the top where we found a way to relate x and y, and we're just going to replace y with that 2 square root 16 minus x squared. And then I'm going to simplify because I've asked you to. And that's our equation for perimeter, right? 4x plus 8 times the square root of 16 minus x squared. Now we're going to go back to our graphing calculator. We're going to graph this and answer the last set of questions for part E. So I've got our perimeter equation typed into my graphing calculator. Make sure you don't have any syntax problems or mistyping. And then I'm going to change the window on this one. I'm going to keep -1 and 5 for the min and max. That matched the min and max on the last set of questions. But I'm going to change the y max to 50 instead of 80. It'll just give us a nicer kind of view. I'm going to hit graph, and we get another weird looking curve like this, which we will sketch in just a minute. But the last part E asks us to use our graphing calculator to plot the perimeter. So remember, now the y values of this function represent perimeters of any of those rectangles that we can inscribe. And we want to use that to find the maximum perimeter of a rectangle we can inscribe inside this ellipse. So again, we're going to find the maximum. You're going to hit second trace. I'm going to go down, select option 4, maximum. And then I'm going to cast kind of a wider net here because I'm not exactly sure where to eyeball necessarily the maximum. So I just want to make sure I find some left bound that I know for sure is below the maximum. I'm going to hit enter, and then I'm going to move this blinking cursor pretty far to the right-hand side because, again, this one is a kind of a flatter curve. It's a little bit more difficult to identify exactly where that maximum is going to be. It looks like it'll be somewhere around 2-ish. But as long as I pick a right bound that's below that maximum, hit enter one more time, it'll find that for us. So I actually overestimated the maximum. It's less than 2 according to our calculator. So our maximum perimeter is 35.777. That occurs when x is 1.78. So let's go back, sketch the perimeter curve, and then answer the rest of these questions. My sketch is in. Again, I just put a single value on the x and the y axis to kind of note the scale there, but a really rough sketch, and then we'll answer the following question. So the maximum perimeter here is 35.77709. We'll round that 8 to get that 7 significant figures. And we're talking about perimeter, so it's just units. Not unit squared because it's not area. And then for what value of x is the perimeter the greatest? Well, that value of x is 1.78885. So that's 7 significant figures. Again, if you're off in like the thousands, the 10,000s, the 100,000s place, it's really not a big deal. You just want to make sure that your calculator is accurate in the first couple of decimal values. If you're really off there, check to make sure that you typed the equation incorrectly in your graphing calculator first. Or redo the maximum value calculation. All right, so that is the maximum perimeter that occurs when x is 1.7888. Okay, so let's just go back to where I had the rectangle and the ellipse drawn for maximum area. So this rectangle in green in the upper right-hand corner of your screen now, that was the rectangle that gave us the maximum area. That was with an x value of 2.82. So let's redraw the rectangle that gives us the largest perimeter. The rectangle that gave us the largest perimeter had an x value of 1.78, so about 1.8. So if I find 1.8 on this graph along the x-axis, it's right there. So if I were to sketch in the rectangle that carries that value of 1.8, this is the rectangle in blue that gives us the max perimeter. So the rectangle that gives us the largest area is not the same as the rectangle that gives us the largest perimeter. So that is it for 210. You guys are going to do your homework the same way. Don't forget to also do the nonsense functions review worksheet on the next page of your student note packet. Bye.